Now in this lecture we'll find out the radius of the circle using two different methods. In the drawing we have triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC, and we know that this angle ABC equals to 60 degrees in its sides, this angle ACB equals to 75 degrees. In addition, we know that side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle. We start with the first method, and we do a construction, that is to say from point C, we do perpendicular on AB. So this angle equals to 90 degrees in its size, this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AB as D. In the next step we will focus on the right triangle BDC, so we'll copy this right triangle BDC in a new page, this right triangle BDC in a new page, and we will analyze it. So actually, this is the right triangle BDC that I copied from the original drawing. Angle CBD equals to 60 degrees according to what is given as the question. BC equals to 2 units, also according to what is given as the question. And this angle equals to 90 degrees according to our construction. In this right triangle BDC, cosine 60 degrees equals to BD over BC. Cosine 60 degrees equals to BD over BC. So it is equals to BD over BC, and BC is 2, and cosine 60 degrees is 1/2. So 1/2 equals to BD over 2. Here we will multiply this equation by 2, and finally we get that BD equals to 1 unit in its length. Let's say that BD equals to 1 unit in its length. So we can write down in the original drawing that this line segment BD is equals to 1 unit in its length. We continue to focus on the right triangle BDC. On the right triangle BDC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC. BC is 2. So in conclusion, we found out that it's equal to 3 over 2 equals to DC over 2. Here we will multiply this equation by 2, and finally we will get that DC equals to the square root of 3 units in its length. Okay, DC, this line segment DC equals to the square root of 3 units in its length. So in the right triangle BDC, this angle equals to 60 degrees, this angle equals to 90 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle must be equal to 30 degrees in its size. And again, in order to complete the sum of the angles in the right triangle BDC to 180 degrees, the missing angle here must be equal to 30 degrees in its size. Angle DCB equals to 30 degrees. So what is the size of this angle? Angle ACD. The size of angle ACD will be equal to the big angle, angle ACB, that is 75 degrees, minus this angle, angle DCB, that is 30 degrees. 75 degrees minus 30 degrees, it is equals to the missing angle, angle ACD. So 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle, angle ACD equals to 45 degrees in its size. So in the right triangle ACD, this angle equals to 45 degrees, this angle equals to 90 degrees. 90 degrees plus 45 degrees is 135 degrees. So the missing angle here must be equal to 45 degrees in its size. Again, in order to complete the sum of the angles in the right triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees. In the next step, I will copy the right triangle ADC in the new page and we'll analyze this right triangle, triangle ADC. So actually, this is the right triangle ADC that I copied from the original drawing. The right triangle ADC, it is also an isosceles triangle. Why? Because those two angles, they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other. That is to say, side AD must be equal to side DC. Those two sides must be equal to each other. But we already found out that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we derive that AD also equals to the square root of 3 units in its length. So here we can write down that side AD, this is side AD, is equals to the square root of 3 units in its length. In the next step, we will continue to focus on the right triangle, triangle ADC. On the right triangle, triangle ADC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem in the right triangle ADC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. So AC square equals to AD square. Here AD equals to the square root of 3. Here AD equals to the square root of 3. So AD equals to the square root of 3, therefore AD square is square root of 3 squared, that is 3, plus DC square. DC is also square root of 3, therefore DC square is square root of 3 squared, that is 3. So in total AC square equals to 3 plus 3, that is 6. AC square equals to 6. We take a root out of this equation and finally we get that AC equals to the square root of 6 units in its length. AC equals to the square root of 6 units in its length. Here, AC equals to the square root of 6 units in its length. In the next step, I will present to you the new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by a triangle ABC, that could be any triangle, is equals to R, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of triangle ABC. This is to say, it is the perimeter over 2. Okay, so here in the drawing we have triangle ABC that could be any triangle. This triangle ABC is block this circle, or this circle is inscribed by triangle ABC. So the radius R of this circle that is blocked by triangle, that is inscribed by triangle ABC, the radius R will be equal to the area of triangle ABC over the semi-perimeter of this triangle ABC. Again, the semi-perimeter of this triangle ABC equals to the perimeter, that is AB plus BC plus AC over 2. We can actually implement rule number 2 in our drawing, rule number 15 in our drawing. Why? Because in our drawing we have this triangle ABC that blocks the circle. Our mission is to find out the radius of this circle. So the radius R of this circle will be equal to, according to rule number 15, the area of triangle ABC over the semi-perimeter of triangle ABC. Repeat again. According to rule number 15, the radius R of this circle that is blocked by triangle ABC, that is described by triangle ABC, the radius R equals to the area of triangle ABC over the semi-perimeter of the same triangle ABC. According to rule number 15, of course. So the area of triangle ABC will be equal to the base of the triangle times the height to the base over 2. Again, the area of triangle ABC equals to the base of the triangle times the height to the base over 2 divided by semi-perimeter S. So we take the base of this triangle ABC as AB, and the height to the base will be CD. Why? Because the height to the base must create 90 degrees with the base AB. You can see that CD creates 90 degrees with the base AB. Therefore, CD is the height to the base divided by 2. Repeat again. The area of triangle ABC equals to the base that is AB times the height to the base that is CD over 2 divided by the semi-perimeter. The semi-perimeter of triangle ABC equals to the perimeter over 2. The perimeter is AB plus BC plus AC. The perimeter is AB plus BC plus AC. If we divide the perimeter by 2, we get the semi-perimeter S. AB, the length of AB is square root of 3 plus 1. times CD. CD equals to the square root of 3 divided by 2. Again, the area of triangle ABC equals to the square root of 3 plus 1 times square root of 3 over 2 divided by the semi-perimeter. The semi-perimeter is AB, that is square root of 3 plus 1, plus BC, that is 2, plus AC, that is square root of 6, divided by 2. Okay, so the area of triangle ABC equals to the square root of 3 plus 1 times square root of 3 over 2. This expression in total it is equals to 2.366 square units, that is the area of triangle ABC, over the semi-perimeter of triangle ABC. This expression, it is the semi-perimeter, and this expression, the value of this expression, it is actually 3.591 units, and 2.366 over 3.591, it is equals to the radius of this circle that is described by triangle ABC. So the radius R equals to 0.6589 units. Repeat again. According to the first method, the radius R of this circle that is described by this triangle ABC, the radius R equals to 0.6589 units. So we finished with the first method. In the next step I present to you how to find out the radius of this circle according to the second method. In the second method, we define the center of this circle, this point, as O. We define the point of tendency of tangent BC with this circle, this point as point D. We define the point of tendency of tangent AC with this circle as point F. And we define the point of tendency of tangent AB with this circle as point E. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, therefore OD equals to R. So here we can implement rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have here line segment A and B is tangent to this circle as point M. Point M is the point of tendency. Tangent AB with this circle. And we have the radius OM is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule number 1. We can implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius OD that is drawn to point D. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees, according to rule number 1. We join points O and D together by a straight line. OE is the radius of this circle, is equals to R. According to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We join points O and F together by a straight line. OF is the radius of this circle that is equal to R. Again, we have the radius OF that is drawn to point F, that is the point of tendency of tangent AC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We have also rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. So here we have this circle and we have this common external point, point P. From the common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, we focus on the common standpoint, point C. From the common standpoint, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD according to rule number 2. Okay. Likewise, we'll focus on the common standpoint, point B. From the common standpoint, point B, we have two tangents to the circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. Again, BD equals to BE according to the same rule, rule number 2. In the next step, we join points O and B together by a straight line. And we join points O and C together by a straight line. In the next step, we will prove that the yellow triangle, triangle EBO, is congruent to the green yellow triangle and to the green right triangle, triangle ODB. This green right triangle, triangle ODB. So I write it down. We'll prove that the yellow right triangle, triangle EBD, it is actually triangle EBO. The yellow right triangle is triangle EBO. Is congruent to the green right triangle, triangle OBD. So why those two right triangles can go into each other? First of all, we just now found out that BE equals to BD. Here, BE equals to BD according to rule number 2. side BE of the yellow triangle equals to side BD of the green triangle according to rule number 2. Repeat again. Side BE of the yellow triangle equals to side BD of the green triangle according to rule number 2. In addition, those two sides, EO and OD, they are both the radii of this circle, therefore they are equal to each other. So, side EO of the yellow triangle equals to side OD of the green triangle. Repeat again. Side EO of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. So they are equal to R. And finally, this is side OB. That is a common side, it belongs to both triangles, so we can write down that OB equals to itself. It's a common side that belongs to both triangles. In conclusion, we found out that all the three sides of the yellow triangle EOB are correspondingly equal to all the three sides of the green triangle OBD. Therefore, those two right triangles can go into each other according to side rule. So write it down. The green triangle EBO is congruent. This is the sign of congruent to the green right triangle OBD. According to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are also equal to each other. So this is angle EBO in the yellow triangle. And it is equal to this angle that is actually angle OBD in the green triangle. Okay, again. Angle EBO in the yellow triangle equals to angle OBD in the green triangle. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So each of those two angles must be equal to theta. If one of the angles is theta, then the other angle must be also equal to theta. So theta plus theta equals to 60 degrees. If 2 theta equals to 60 degrees, according to what is given as the question, we divide this equation by 2 and finally we get that theta equals to 60 over 2, that is 30 degrees. So actually this is angle theta is equal to 30 degrees in its side. In the next step, we'll focus on the green right triangle OBD, so I'll copy the green right triangle OBD in the new page and we'll analyze this green right triangle OBD. So actually, this is the green right triangle OBD that I copied from the original drawing. This right triangle OBD tangents 30 degrees equals to OD over BD. So tangents 30 degrees equals to OD, that is R, over BD. So here tangents 30 degrees equals to R over BD. Here we multiply this equation by BD, and we get that BD times tangents 30 degrees equals to R. Here we divide this equation by tangents 30 degrees, and finally we will get that BD equals to R over tangents 30 degrees. So this line segment BD equals to R over tangents 30 degrees in its length. Okay. In the next step, we'll prove that the orange triangle ODC. This is the orange triangle ODC. Is congruent to the pink triangle OFC. So I write it down. We prove that the pink triangle ODC is congruent to the pink triangle OFC. So why those two triangles can go into each other? First of all, CF equals to CD. Here CF equals to CD according to rule number 2. Repeat again. Side CF in the pink triangle equals to side CD in the orange triangle, according to rule number 2. In addition, those two sides, they are both the radii of the circle, therefore they are equal to each other. Side OF in the pink triangle equals to side OD in the orange triangle. They are both the radii of the circle, therefore they are equal to each other. Repeat again. Side OF of the pink triangle equals to side OD of the orange triangle. They are both the radii of the circle. Each of them is equal to R, the radius of the circle. And finally, this is side OC. It is a common angle. It is a common side that belongs to both triangles. Therefore, we can write down that OC equals to itself is a common side that belongs to both triangles. So actually proved that all the three sides of the pink triangle OFC are correspondingly equal to all the three sides of the orange triangle OCD. Therefore, we proved that the pink triangle OFC is congruent. Again, this is the sign of congruent to the orange triangle ODC. According to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So this is angle FCO in the pink triangle. And it is equal to this angle OCD in the orange triangle. So if we define one angle as alpha, then the other angle must be also equal to alpha because those two angles are equal to each other. So alpha plus alpha equals to 75 degrees according to what is given as the question. So 2 alpha equals to 75 degrees. We divide this equation by 2 and we get that angle alpha equals to 75 degrees over 2, that is 37.5 degrees. So this is angle alpha that is equals to 37.5 degrees. In the next step, I will copy the orange triangle ODC. In the new page, we will analyze this orange triangle ODC. So finally, this is the right triangle ODC that I copied from the original domain. This is angle alpha that is equals to 37.5 degrees. And side OD is the radius of this circle that is equals to R. So in the right triangle ODC, tangents 37.5 degrees equals to OD over DC. So tangents 37.5 degrees equals to OD, that is R, over DC. Again, tangents 37.5 degrees equals to R over DC. Here we multiply this equation by DC and we get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees and finally we get that DC equals to R over tangents 37.5 degrees. Repeat again. We actually found out that DC equals to R over tangents 37.5 degrees. So we can write down the original drawing that line segment DC equals to R over tangents 37.5 degrees. This is line segment DC, and it is equals to R over tangents 37.5 degrees. Okay. So here it is very easy to see from the drawing that side BC equals to BD plus DC. Again, BC equals to BD plus DC. So I write it down. BC equals to BD plus DC. Okay, again, from the drawing it is very easy to see that BC equals to BD plus DC. So BC and BC is 2 according to what is given in the question. So we substitute BC by 2. So 2 equals to BD. We have already found out that BD equals to R over tangents 30 degrees. So we substitute BD by R over tangents 30 degrees. Plus DC. We already found out that DC equals to R over tangents 37.5 degrees. So we substitute DC by R over tangents 37.5 degrees. So in conclusion, found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. So 2 equals to, we take R as a common factor out of those two expressions. Here, after we took R as a common factor from this expression, we left only with 1 over tangents 30 degrees. Plus, after we took R as a common factor from this expression, we left here with 1 over tangents 37.5 degrees. So 2 equals to R times 1 over tangents 30 degrees plus 1 over tangents 37.5 degrees. So 2 equals to R. Inside the brackets we have 1 over tangents 30 degrees equals to 1.732 plus R over tangents 37.5 degrees. 1 over tangents 37.5 degrees equals to 1.3032. So actually found out that 2 equals to R, and 1.732 plus 1.3032 is 3.0352. So actually found out the 2 equals to R times 3.0352. Here we divide this equation by 3.0352, and finally we get that R equals to 2 over 3.0352. Repeat again, we actually found out finally that the radius of the circle that we are looking for, R, the radius R, equals to 2 over 3.0352. 352, and this expression equals to 0.6589. So actually found out that the radius of the circle that we are looking for is equals to 0.6589 units. So in both methods, we actually found out that the radius R of this circle that is described by triangle ABC equals to 0.6589 units. In the next step, I will summarize the lecture. We start with the first method. In this lecture, we found out the radius of this circle that is described by triangle ABC, or triangle ABC blocks this circle. We know that this is angle ABC, it is equal to 60 degrees in size, and this is angle ACB, it is equal to 75 degrees. In addition, we know that side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is described by this triangle ABC. In the first method, we did a construction, that is to say from point C we drew perpendicular on side AB. So here, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AB as D. So we created here the right triangle DBC. So we copy the right triangle DBC in a new page and we analyze this right triangle DBC. Usually this is the right triangle DBC that is coming from the original domain. In the right triangle DBC, cosine 60 degrees equals to dB over BC. Again, cosine 60 degrees equals to BD over BC. So it is BD over BC, and BC is 2. So in conclusion, we found out that cosine 60 degrees equals to BD over 2. Cosine 60 degrees is 1/2. So 1/2 equals to BD over 2. 1/2 equals to BD over 2. We multiplied this equation by 2 and finally found out that BD equals to 1 units. Here, this line segment BD it is equals to 1 unit in its length. We continue to focus on the right triangle BDC. On the right triangle BDC, sin of 60 degrees equals to DC over BC. Again, sin of 60 degrees equals to DC over BC. Sinus 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to DC over BC. And BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally found out that DC equals to the square root of 3 units in its length. Here, this line segment DC equals to the square root of 3 units in its length. So in the right triangle DBC, this angle equals to 60 degrees. This angle equals to 90 degrees. 60 degrees plus 90 degrees, it is 150 degrees. So the missing angle here must be equal to 30 degrees. In order to complete the sum of the angles in the right triangle DBC, this right triangle DBC to 180 degrees, this missing angle must be equal to 30 degrees. So it is given us the equation that the big angle ACB equals to 75 degrees. So the big angle ACB that is 75 this angle that is 30 degrees must be equal to the missing angle here. Angle ACD. So angle ACD equals to 75 degrees plus 30 degrees, it is 45 degrees. The missing angle ACD equals to 45 degrees in its size. So I copied the right triangle, triangle ADC in a new page, and analyze this right triangle, triangle ADC. This is actually the right triangle ADC that I copied from the original drawing. DC equals to the square root of 3 units, according to what we already found out. And we know that this angle equals to 90 degrees. This angle equals to 45 degrees. 45 degrees plus 90 degrees, it is 135 degrees. Therefore, the missing angle must be equal to 45 degrees in its size. Again, in order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle must be equal to 45 degrees. So those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. AD must be equal to DC. But we already found out that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that side AD also equals to the square root of 3 units in its length. Yeah, this side AD equals to the square root of 3 units in its length. Okay, then we continue to focus on the right triangle, triangle ADC. On this right triangle, triangle ADC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. Again, AC square equals to AD square plus DC square. AC square, that is the square of the hypotenuse, equals to AD square. AD is square root of 3, therefore AD square is square root of 3 squared, that is 3, plus DC square. DC is square root of 3, therefore DC square is square root of 3 squared, that is 3. So in total, AC square equals to 3 plus 3, that is 6. AC square equals to 6. We took a root out of this equation and finally found out that AC equals to the square root of 6 units in its length. Yeah, this side AC of triangle ABC equals to the square root of 6 units in its length. Okay, then I presented to you a new rule and implemented the new rule in our drawing. The new rule, it is actually rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to R. The radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC that blocks the circle. The semi-perimeter is S. And the semi-perimeter of any triangle equals to the perimeter over 2. So here we have triangle ABC that could be any triangle. This triangle ABC blocks this circle, or this circle is inscribed by this triangle, triangle ABC. So the radius of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Again, the semi-perimeter is the perimeter that is AB plus BC plus AC over 2. You can actually implement rule number 15 in our drawing. Why? Because in our drawing we have the right triangle ABC that blocks this circle. Of this circle is inscribed by the right triangle, triangle ABC. So according to rule number 15, the radius of this circle will be equal to the area of triangle ABC over the same perimeter of the same triangle, triangle ABC. I'll repeat again. According to rule number 15 in our original drawing, the radius of the circle that is described by triangle ABC equals to the area of triangle ABC over the same perimeter of the same triangle, triangle ABC. So the radius of the circle R, the radius R equals to the area of triangle ABC. The area of any triangle equals to the base of the triangle times the height of the base over 2. The height must create 90 degrees with the base, all divided by S, that is the same perimeter of the same triangle, triangle ABC. So here we took the base of this triangle ABC as AB, and the height is DC. Why? Because the height DC creates 90 degrees with the base. So the base is AB, the height is DC over 2. So in total, now on triangle ABC equals to the base AB times the height to the base, that is CD, over 2, over the semi-perimeter of the same triangle ABC. The semi-perimeter of this triangle ABC equals to the perimeter, that is AB plus BC plus AC, over 2. Again, the semi-perimeter S of the triangle ABC equals to AB plus BC plus AC over 2. Okay, so we have already found out that AB equals to the square root of 3 plus 1. Here, AB equals to the square root of 3 plus 1 times CD. CD equals to the square root of 3. CD equals to the square root of 3 divided by 2. And the semi-perimeter of triangle ABC equals to AB, that is square root of 3 plus 1, plus BC, that is 2, plus AC, that is square root of 6, divided by 2. This expression in total equals to 2.366, and this expression, that is the semi-perimeter of the triangle ABC, it is equals to 3.591. 2.366 over 3.591 equals to the radius of the circle that we are looking for. That is actually 0.6589 units. So the radius of this circle, according to the first method, the radius R equals to 0.6589 units. We finish with the first method. In the next step, actually presented to you how to find out the radius of this circle according to the second method. In the second method, we defined the center of this circle here, this point as O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, D is the radius of this circle, that is equal to R according to our definition. We have the radius R, the radius OD. That is R, it is known to point D, that is the point of tendency of tangent BC with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We join points O and D together by a straight line. OE is the radius of this circle, and we have the radius OE that is known to point E. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points O and F together by a straight line. OF is the radius of this circle that is equals to R. The radius OF is known to point F. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then we implemented in our drawing rule number 2. We focus on the common extent point C. From the common extent point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD according to rule number 2. Likewise, we focus on the common extent point B. From the common extent point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. Here, BE equals to BD equals to BE according to the same rule number 2. Then we join points O and B together by a straight line, and we join points O and C together by a straight line. In the next step, we proved that the yellow triangle EOD is congruent to the green triangle, triangle OBD, while those two white triangles can go into each other. First of all, EB equals to BD according to rule number 1. EB equals to BD according to rule number 1. In addition, those two sides are both the radii of the circle, therefore they are equal to each other. And finally, we have here side BO is a common side that belongs to both triangles, so we can write down that side BO equals to itself is a common side that belongs to both triangles. So I shall prove that all the figures of the yellow triangle EOB are correspondingly equal to all the figures of the green triangle BOD. Therefore, we prove that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if one angle is theta, then the angle must be also equal to theta because they are equal to each other. That is to say theta plus theta equals to 60 degrees according to what is given as the equation. Here, theta plus theta, that is 2 theta equals to 60 degrees. We divided this equation by 2 and found out that theta equals to 30 degrees in its side. This is angle theta, that equals to 30 degrees. This is angle theta, that equals to 30 degrees in its side. Then I copied the green right angle OBD in the new page and we analyze this green right angle OBD. This is the green right angle OBD that I copied from the original domain. This is angle theta, that is equal to 30 degrees in its size. OD is the radius of the circle that is equal to R. So in this right triangle OBD, times 30 degrees equals to OD over BD. That is to say it is equals to OD, that is R over BD. Here times 30 degrees equals to R over BD. Here we multiply this equation by BD and we found out that BD times 30 degrees equals to R. Here we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. Here this line segment BD equals to R over times 30 degrees in its length. Then repeat it on the same process on those two triangles, the orange triangle and the pink triangle. We proved that those two triangles can go into each other according to side rule. Again, we have side FC, that is equal to, side CF equals to side CD. Here CF equals to CD according to rule number 2. In addition, those two sides are both the radii of the circle, therefore they are equal to each other. And finally, side OC is the common side that belongs to both triangles, so side OC equals to itself is the common side that belongs to both triangles. So we actually proved that the pink triangle OFC, all the three sides of the pink triangle OFC are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, we proved that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha, that is 2 alpha, equals to 75 degrees according to what is given as the question. Here, 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. This is angle alpha, that is equals to 37.5 degrees. Then I copied the orange triangle ODC in a new page and we analyze this orange triangle ODC. This is the orange triangle ODC that I copied from the original domain. Side OD equals to the radius of the circle, that's equal to R. This is angle alpha, that is equal to 37.5 degrees. In this right triangle ODC, times 37.5 degrees equals to OD over DC. Again, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So times 35 degrees equals to R over DC. Here we multiply this equation by DC and found out that DC times 37.5 degrees equals to R. Here we divided this equation by times 37.5 degrees and finally found out that R equals to times 37.5 degrees. The DC equals to R over times 37.5 degrees. Here, this is side DC, this equals to R over times 37.5 degrees. From the domain itself, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Repeat again, BC equals to BD plus DC. BC is 2, according to what is given as the equation. BC is 2. BD is R over tangent 30 degrees. Here BD is R over tangent 30 degrees plus DC. DC is R over tangent 37.5 degrees. Again, DC is R over tangent 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. Here we took R as a common factor from those two expressions, and we found out that finally that 2 equals to R is a common factor, so inside the brackets we left only with 1 over tangent 30 degrees plus 1 over tangent 37.5 degrees. So 2 equals to R, and 1 over tangent 30 degrees is 1.732 plus 1 over tangent 35 degrees is 1.3032. So 2 equals to R plus 1.732 plus 1.3032. And 1.732 plus 1.3032 equals to 3.0352. So in conclusion, found out that 2 equals to R times 3.0352. So we divided the equation by 3.0352 and finally found out that R equals to 2.30352. That is actually 0.6589. So the radius R of this circle that is described by triangle ABC equals to 0.6589 units. Again, the radius R in both methods of this circle that is described by triangle ABC equals to 0.6589 units. Okay, thank you very much.